In this video, we will begin looking at differential equations, and we'll just be taking an introductory look. Differential equations is a really big topic. Entire books are written just on this one topic. But we'll just be looking at an introductory level and seeing what differential equations are and how they are solved. And I'll start off by putting an example of one on screen here. AX equals dx dt. Now take note, here's x, and here's the derivative of x with respect to t, and we can think of t as being time. That's often the case. So the fact that x has a derivative with respect to t implies that x is a function of t. This x right here isn't simply a variable. It's a function, and in this case it's a function of t, or a function of time. So the essential aspect of a differential equation is that a function and its derivative both show up in the equation. That's what makes it a differential equation. So remember that x here isn't just a variable that can have a value. X is a function, and the function and its derivative show up in the differential equation. Now if we want to solve this for x, that means we need to find the function x that satisfies this equation. So solving the differential equation doesn't mean we find the value for x that works. We find the function x that works. So this is a little bit different than solving simple equations like we did way back in Algebra 1. For example, if you had this, x plus 4 equals 10, and you want to solve this equation, that means finding the value for x that makes this equation true. And obviously x equals 6 is the solution, because if we plug in a 6 right there for x, then that's a true statement. This is different. We're not finding a value, we're finding a function. X is a function of t. So solving the differential equation means to find the function which will satisfy that differential equation. And since derivatives show up in differential equations by definition, the solution, or finding the solution to a differential equation, often involves integration. Now here's a multiple choice question. Differential equations are A, not really all that important, or B, a really huge, gigantic, tremendously important, big deal. Let's see. We'll check box B right there. Differential equations are very important. In fact, differential equations are really the equations that most naturally describe processes in the real world. When you look at the world, and especially when you look at it in terms of physics, you naturally come up with differential equations to describe processes and things that you see going on in the real world. And solving the differential equations is what often leads to good theories of physics that describe good and useful theories that describe things that are going on in the real world. And we'll see examples of this as we go through this material. We'll see how differential equations arise from an understanding of the natural world, especially in terms of physics, and how solutions to them provide us with equations that describe how things actually behave in this world. In college, if you study physics or engineering, you'll probably have an entire course on differential equations. A typical college math sequence might look like this. You have Calculus 1, which is integral calculus, or differential calculus, and then Calculus 2, which is integral calculus, integration, and then Calculus 3 is typically multivariable calculus, and then differential equations, which is commonly referred to as DE. So that's typically where it falls in a college level math sequence. Now, as our first example, I'm going to show you a differential equation that arises from Hooke's law. So first, of course, we need to make sure that everybody knows what Hooke's law is. This is named after Robert Hooke, the physicist who lived at the time of Isaac Newton, although Newton really didn't like Hooke. Hooke was actually the guy that kept Newton out of London, not intentionally, but Newton just detested him so much that Newton stayed in Cambridge for decades and didn't move back to London until Hooke died. Newton, being the incredibly introverted person he was, didn't really like people at all, so he just stayed out of town until Hooke died. But this is one of the ideas that Hooke came up with. This explains the force in a spring. This is a wall over here, and let's suppose we have a spring attached to the wall like this. And we grab the spring here and we pull it out this way, some distance x, and when we do that, the spring pulls back. So there's some some force back in this direction, F. And Hooke's law says that F equals negative kx. Now this should make sense intuitively. You've all stretched a spring before, or something springy like a rubber band, and you know the farther you stretch it, the more force is required. So the force is proportional to the distance, like that equation says. And if we pull it to the right, it pulls back to the left. So the distance x and the force that the spring is pulling are in opposite directions, and that's why we have the negative sign. So this makes sense intuitively, and it also matches the empirical evidence. As long as we don't stretch the spring beyond what's called the elastic limit of the spring, then it's going to behave in an amazingly linear fashion, just like this equation implies. Okay, now imagine this. Imagine we have a wall and the floor, and here's our spring attached to it. And then let's suppose we have this mass on the end of the spring. It's resting on the floor there. I'm going to extend the floor a little bit. Okay, so there's a mass M, and suppose we pull it out a distance x. So we pull it out some distance x, and we release it. And there's going to be a force pulling back from the spring. And we're going to assume that there's no friction here, so it slides freely across the floor, although we certainly could include the case that involves friction, and we would do that later on, but we'll do the simple case first where there's no friction. Well, we know Hooke's law tells us that F equals negative kx. This is an accurate description of what's going on with this force and this distance. But we also have an M here, a mass. And when you think about a force acting on a mass, what typically comes to mind is Newton's second law. Newton's second law says F equals ma. Okay, so here comes the differential equation. If we start off saying F equals ma, and we also know that F equals negative kx, then we can say that ma equals negative kx. And I know that a, the acceleration, is the second derivative of position. So I can write this. I can write m times the second derivative of x, d squared x dt squared, equals negative kx. And look at this. Here's x, and here's the derivative of x. Actually, the second derivative of x. But we have x and its derivative showing up in this equation. This is a differential equation. And it shows up naturally from our understanding of physics. In this case, the physics involving the force in a spring and Newton's second law. And it should make sense to you that x is a function of time. If we pull this out a certain distance x and release it, the spring's going to pull it back. And as it pulls back, it's going to gain some momentum back toward the wall, but it's going to get up enough speed to overshoot the point at which it started, and it's going to go toward the wall, compressing the spring. And as the spring compresses, it's going to exert a force back to the right. And that's going to cause it to slow down and stop and move back to the right. And it's going to oscillate back and forth, and that should make sense. You pull this out and it goes boing, 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 back and forth. The frequency at which it oscillates is going to depend on the mass and the stiffness of the spring. But it's going to be a function of time. X is a function of time, and this is the differential equation which describes this situation. Now, we could do some math to solve this equation. We could find a function x being a function of time that satisfies this differential equation. The math to do that is fairly difficult, but the solution is not that bad. I'll show you what the solution is. If we did the math to solve this, the solution would be x is equal to x0, that's the initial position, times the cosine of the square root of k over m times t, where k is the stiffness of the spring from that equation, F equals negative kx, and m is the mass. So the position x here is a function of time. And we could differentiate this twice. We could find the second derivative of that and show that it satisfies this equation. And that's not too hard to do. Getting to this equation from here is a little bit more advanced than we're going to do right now, but we'll come back in some of the exercises and at least show that this does in fact satisfy that equation. Now in the next video I'll show you another differential equation that shows up in the real world, and we'll actually work through the solution and show how you get from the differential equation to the solution.